Okay, I guess we slowly starting. Let me just like double check that all things connected. I see from StreamYard that looks like started, and also on YouTube it's like working well. Cool. So yeah, welcome everybody for this new edition of Hacking Machine Learning. This is like one of those editions when we do it from home, right? And yeah, it's interesting because I think on one hand it's definitely a different setup, right? We have like a like different surroundings around us, right? Maybe there's like not so many people with beers and pizzas, and it's just a different feel to this one. But it's definitely like enabling us to have like completely different diverse like set of people, right? Because for instance today we definitely have people just like happen to be most of them working at Google, but it's also like a different geography, right? So Karl is working from United States, right? And actually having today the Thanksgiving, and Anant is working from Munich. So I'm really happy that we are able to actually join applications as well. And hopefully the same goes for you, right? You don't have to be in Munich in order to watch us, right? And you can be joining from any location, from any exciting weather, right? Or scenery that like just next to you. But if you're watching it like on YouTube, maybe comment in the section like on the right side from what location you're watching. It would be interesting to see geography of this one. So a couple of organizational questions before we jump into the talks while you're here, just to understand how things are structured and how you can better find information. So first of all, we're using Meetup as a source of us getting organized, right? Meaning, so here you can find like our next events, and you can sign up like just in time before this one. We also use we use Slack, or use Slack. And the idea of this one is that it's not only that you're meeting once a month or once a couple of months, depending like of a schedule, but you actually have a connection to each other on way more continuous basis, right? And the idea of that being that we hope that by you learning together, right, you're finding like a new maybe teammates, right? Maybe people working on different projects. You can keep this connection and maybe develop yourself like even better than before. Just like a word of history, that's how it looked like before March, I guess, because before February like 2020, when we still used to meet up like in nice locations, like with offline setup, right, and without any social distancing. Now it's how it's like looking actually for me today. I have like a screens, right, and I have like laptop, but I still have like amazing people next to me. I mean, next in this case, just like via the same video, but it's definitely giving some opportunities. And since we're coming from different, as I said, geographical point of view, points on the map, right, it's also like a different backgrounds that we're bringing, right? And I wanted to congratulate or thanks our people who's celebrating Thanksgiving today, because first of all, you did a great job like over the last 12 months, and especially to the Karl who is joining us from giving a bit of time like from family to community, right? It's like super appreciated. I'm like really like what you're doing that. And without some graph, right, for machine learning and data science, it wouldn't be as the same as just like showing food. So here's just like another point about Thanksgiving. So what I'm trying also to do is get our slides of speakers on Meetup. There are not all of them are like yet, but we definitely would like to get this one on Meetup, so you can get the slides like afterwards. If there's something missing, just like ping me or speakers, and we will try to add it. You can also send a pull request, right? So it's all public. Yeah, and today we have pretty interesting talks, right? And what all this about, right? Is on one hand, machine learning is getting like quite a bunch of hype recently, right? And there's like if you go on YouTube, just like on the internet, there's like many tutorials, right? There's many one-on-one sessions, right? Like how to get, training your classifiers, right? How to get things like going, right? In reality, if you would like to get it to production within your company, or I don't know, like build a startup around this fun, it suddenly becomes like not so easy, right? It becomes like completely different set of the problems, right? And I almost like have a feeling that sometimes we as a community a bit of like overly focusing on state of the art, right? I mean, this is like super helpful, but in many cases there is like still entire universe between like you having very solid algorithm, right, and you actually bringing this value to the users who need it, right? And today we have like two speakers like bringing actual learnings, right? What can go wrong with machine learning projects, right? What you should take care of, right? And what are those like tiny but yet like super helpful changes, right, that would enable the value for your stakeholders, right? Because at the end of the day, it's kind of cool to do machine learning for sake of doing this one, right? You can definitely do research, but if you want to change life of like millions, right, it's also good to start applying that, right? So in the beginning, as I said, it's going to be, we start with a talk from Karl from Google, and he's bringing like many ideas of like MLOps, right? Transparency, fairness, model accuracy, and how you can combine those things together. Fun fact about Karl, he was actually one of first people who started to use like AI for solving like crosswords, right? And he's still getting quite a bunch of attention. So definitely follow him on Twitter or in other channels to get information. Another person who I'm like super happy to have here is Anant. Anant is also working today, as I'm concerned, at Google Munich. But he did also quite a bunch of machine learning and like at other companies like Amazon and before as well. And he's also bringing like a couple of like horror stories about dirty data, right? How to overcome it, right? What are the tricks and tips you can get in order to avoid those problems? And yeah, really looking forward to see both of those talks and how it's gonna also make you a better practitioner, right? And maybe make you more valuable for things that you're doing. Yeah, before I'm going to finish this part, I would like to say that usually if you do like offline, we're also happy to get support from you, right? And I mean, like how we can support people in offline is usually like pizza location. With online setup is a bit harder. But if you would like to support your local machine learning community, maybe reach out to me and we can figure out how to enable our folks like a bit better. Sometimes I would like to also give a bit of sneak peek of what is cooking, right, and what is exciting we would like to share or what we have on our plate. And this time we actually planning something for pretty soon, like it's almost like in 2 weeks, right, on December 10th. And there we would like to go beyond supervised learning, right, because there's quite a bunch of discussions going like around contrastive representation learning, right? And I wanted to bring actually somebody from quite a bit of experience like doing this one, and that's going to be the next event. So on one hand, please sign up for this event on Meetup, right? And looking forward to having you. But also, if you did some work related to this one, please ping me on I don't know, any of channels that you use, right? And I'm happy to have you as a speaker. Because at the end of the day, all of this community, right, is like nothing. There is no like me and you, right? It's like community by community. So basically, just reach out if you have talks. More than happy your get shared, right? Because even if you have 15 minutes talk, right, that is just a light talk, just that you might be saving somebody like days and weeks of time working on something. So it's definitely valuable. Don't be shy of sharing your amazing knowledge. And if you just want to make this better as a volunteer, because you want to, I don't know, ensure that we uploading slides on GitHub, right? Or finding like cool speakers or anything that would be helpful for remote machine learning community during such shaky times, just like reach out to me and I'm happy to have you. Yes, with that, I'm kind of like done with my intro part. And I will just welcome Karl to the stage. So please give him a round of virtual applause. And I will get my screen off and get Karl to the screen. Hey. Awesome having you.
Happy to be here. Thank you. And just want to say, this is my first time talking to Hacking Machine Learning. Nice to meet all of you. I know we're all in a challenging time with the pandemic, but it's nice to have this opportunity to work with some new communities I haven't, and hopefully in the future I'll be able to visit Munich in person and meet some of you. and wherever you are in the world.
That would be amazing.
All right. Yeah. So let's get started. So just a quick introduction. I wanted to talk to you about some challenges that I've seen myself. Prior to coming to Google, I was working in machine learning, running projects, seeing firsthand some of the issues that people can run into. And now being at Google, I work with customers all the time. I see a variety of challenges, and I just wanted to share some of the issues I've seen with all of you, have a great discussion, and go from there. So let's start with the presentation. Again, I want this to be interactive. We're going to go through a lot of information, but there should be time at the end to kind of, discuss any scenarios you've run into or any questions you might have. So let's get started. One moment. Okay. Here we are. And Sergey, don't be shy about interrupting me if there's any technical challenges. So our topic today, 10 things that can go wrong with ML projects. So there, of course, are more than 10 things, but I wanted to pick 10 that I have personally run into and I think that are critical. Also, we're not just going to talk about what can go wrong. We're going to look at some of the solutions, and those solutions could either be through best practices, or they could maybe in some cases there are tools that can help you with these issues. Okay, so the first one. So here's the landscape of the different issues. They kind of fall into a few buckets here. Building the model. Once you build a model, getting to the right level of accuracy. Then we'll move on to issues of transparency and fairness. And finally, putting the model into production with MLOps and some of the challenges you could see there. So let's start with building a model. So it all starts with solving the right problem. So here in the graphic, we see the expression that if your only tool is a hammer, every problem looks like a nail, right? So it's important that we really are solving the right problem with machine learning. There's so much hype out there. So we're seeing some organizations just completely change, and they're seeing incredible results out of machine learning. And in some cases, we see some organizations struggling where they're not quite seeing the value out of that investment. And I think that there are some questions that you can ask yourself and the team to wonder what really is the goal here, right? The machine learning model that you're building is just a way to get there, but making sure you're clear on that goal. Secondly, what level are you trying to reach? Often it's a little bit fuzzy of where do you stop? What's good enough, right? And so knowing what your baseline is, which in some cases could mean what kind of answers do you get without machine learning? And then once you add machine learning to the equation, how does it compare against that? These are some of the things to think about. One video that I would recommend I'm putting here is from Google DeepMind. It's about product management for AI. And this video is from a product manager in the DeepMind area that's a research group within Google. And it's really interesting to me because there's, in research, right, you're a little less tied directly to your users. And so this talk gives us some really good tips for how to adjust and stay focused as you're discovering what your goals are here on the project. So I highlight a couple insights. One is be crystal clear on the goal of your project, but be flexible on the tactics to get there. Don't get stuck on one particular type of model or framework. Just be ready to adjust. Second, similar, set some milestones for your project. I know that it's tempting to say, well, we're in a discovery phase, or we really don't know much about what to expect, so I'm not comfortable creating deadlines yet. Well, try to time box your project, create some milestones, but be flexible on those as well if you learn new information. We'll talk a little bit later about prototyping and the value of that. The final thing is making sure your users are central to each stage of the project. You are not losing sight of them. They're involved. You're showing them what you're doing as you go. You're continuing to interview them. to help be the North Star to ensure that you are solving the problem correctly, having maximum impact. So great video, recommend watching that one. Oh, let's keep moving. Another thing to think about is your problem a good fit for machine learning, right? Machine learning, can do a lot of things very well, but again, we have to be careful of it, the hype where you just, sometimes the management team might think you just apply machine learning and everything changes. So here are a few classes of problems. This is not, of course, the whole set of things it can do, but here's a few common buckets, right? One is predictive analytics, and this is where we look at historical data and we predict what might happen next. And that could be a couple examples here, say fraud detection, where you're looking at a history of different amounts, locations, et cetera, and it might be a supervised learning problem where you're trying to predict whether future transaction is fraudulent or not. Another could be predictive maintenance, where we're looking at metrics on from a sensor like heat and vibration and things like that, and trying to see if we can predict if some equipment is going to go bad before it actually goes bad. The whole set of problems around that. Another is unstructured data. So maybe you want to cluster information to better focus on what you need to triage, right? So we can look at videos, pictures, emails, etc. Automation is another key use case, right? Where can we take a tedious or error-prone step of a process and use machine learning to basically solve the problem and handle it automatically for us. And finally, personalization. Maybe there's a way that you can understand your user a little bit better and help provide more helpful information in your application for them. Okay, so that's about solving the right problem. Let's move on to the next problem, which is jumping into development without a prototype. And I think this goes hand in hand with solving the right problem, is that we don't know all the answers at the beginning of the machine learning project. So think of it as an iterative, agile process. Start with something simple and continue to refine that. And also consider having a prototype to just say, we're going to create a short time-boxed exercise where we're going to try to solve it within a period of weeks. And then we're going to learn a lot along the way. We're going to learn about maybe some requirements that we didn't know existed. Maybe we're missing data that's necessary, or we've got dirty data. Maybe we learn about how to scope the project, what's the complexity, the timing a little bit better. And that will allow you to have more certainty as far as the rest of the project. So consider having a prototype phase there. So there's a couple ways you can do that. I'm going to, again, mention some Google Cloud technologies, but really some of these ideas are universal. So if you've ever happened to use BigQuery before, a data warehouse where you can take all of your analytics data into it as a starting point, it's got some really interesting capabilities where you can, if you're comfortable with SQL to write, select statements, you'll be able to very easily create all kinds of models, from deep neural nets to even does some time series, ARIMA models, things like that, all within BigQuery. So you can get some fast prototypes in the same place that you were storing your data. Another option could be AutoML, where you're able to build a model without having to actually write that model code. You just bring your own data, and then those kind of middle steps that you see here in this diagram, training, deploying, and serving the model, are handled by AutoML. It's going to search across a broad variety of frameworks, hyperparameter tuning, ensembling to find a great model for you and then host it for you. So that can, again, help. And it's not limited to the prototyping phase, but it's a great way to check your work, get a baseline, and then see if you might be able to exceed that. Okay, problem number 3, model training can take a long time. And I'm sure this is a common one where you have to wait a day or hours, and that just really slows down innovation. Wouldn't it be nice if, like when you're coding things, sometimes you can just save and quickly compile, deploy your web application, see the result. Okay, there's a problem. Let me change something, redeploy, see the result. When you have to wait hours, you might switch to a different topic, get distracted, and it really just slows down everything. So if there's a way that you can potentially speed up that training time, it can really help you try more ideas out and move faster. One solution to that is distributed training. So for instance, with the AI platform training service, you can submit a training job and not worry about the infrastructure. You can use TensorFlow or XGBoost, a variety of different models, provide your own Docker container, and it will help with that. And then take advantage of some of the specialized hardware, so you can use GPUs, for instance, to finish your job faster. Another cool thing that it has is hyperparameter tuning. So you can provide a YAML file that says, here are the parameters that I want you to do a search. Let's put different ranges of learning rates or other parameters, and it will handle that for you and show you the accuracy for those just different combinations in the web console. Another option could be trying out TPUs to run very large training jobs. They are becoming a lot more accessible with TensorFlow 2.1 and then 2.3 recently. Really, it's just a couple more lines of code. There's a TensorFlow TPU strategy that you would use, just like if you're running like the mirror strategy or some of the others. You kind of wrap some of the model compilation code in that, and you might also point from your notebook to the IP address of the TPU, and it's going to run on the TPU. So it's again become quite straightforward to use now. Can really speed up those training jobs. Okay, let's talk about model accuracy next. So this is probably a common one if you're doing classification. You have an imbalanced data set. The samples that you have, the number in one class or the other are way off, right? I mentioned fraud detection before. So this is a typical example of that, where most transactions are benign. There's no issues with them. And then a very small amount are fraudulent. And so often what models are doing are optimizing for the accuracy across the whole data set, right? So if you think about it, if your model was as simple as just saying every transaction is benign, you're going to get, in this case, if 99% of transactions are benign, you'll get 99% accuracy, but that doesn't mean your model does anything. So you really want to look carefully at how is your model doing across every class, and how do you handle the cases where you have much less data to work with in some of your classes. So I just wanted to point out here a tutorial from TensorFlow that has some great example code of how to handle that. I mentioned some solutions here to consider. So sometimes you can weight each class. So you can basically provide more of a penalty for errors on one particular class to help with that. Another way to handle this is oversampling and undersampling. So you could potentially maybe have twice the number of samples in your, basically double or triple the number of samples in your minority class to kind of bump up that number and help with the weighting. Another option is undersampling, where you might actually reduce some of the examples from the class that has more in it. Undersampling, I personally haven't seen giving great results. Oversampling may have some benefit, you'd have to see. Another option is generating synthetic data, so that there are some packages that can actually, one's called SMOTE, S-M-O-T-E, for instance, and it can look at the structure of your data and kind of the distribution and create some new synthetic data that might help to kind of help balance it. Again, I've had mixed results with that, but it's, and that might just be I didn't quite get the right parameters set. These are all different things you could try to help with imbalanced data. Of course, getting more of the minority class is always a good thing to help solve that at the root. But if you can't, here are some ways to help with that. I wanted to mention in AutoML, there are some things that you can do that can help with this issue. So when you train with AutoML, you basically have a couple steps. It's pretty straightforward. You import your data, you select what column are you targeting, and then it trains your model. As you see here in the screenshot, there's also an advanced options tab. If you open that, you'll see that there's an optimization objective you can set. And this is where you, depending on your objectives, you could adjust this optimization objective, right? So you can see that, say, log loss might just kind of optimize across the whole data set, but you also can maximize the area under the curve using, the ROC curve or a precision recall curve, and each kind of has different, different results. So you can kind of play with that and see what kind of results you're getting across your different classes. So here's kind of an idea too. Once you build a model, this is what you might see in the case of a classification problem. We'll kind of walk through 1, 2, and 3 here. So there is a threshold, right? So as you're distinguishing between the classes, you can set what that threshold is. So you can play with that slider to try different thresholds, getting different precision recall metrics. Another thing you can do is look at your confusion matrix. So here in this example, we're predicting whether a flight is going to be on time or being delayed. And we have a very similar issue here because most flights are on time and we can predict those pretty well. It looks like 97% of the time we are. It's trickier with the delayed flights. We just have much fewer instances of that, right? So we can look at this confusion matrix and kind of see how that, it's playing out across all of our different classes. So, after you go through this process, you could also update that optimization objective, build a different model, and see how these metrics play out. Okay. All right. So let's run into another issue here where, you've tried AutoML or you've built your own models and you really just get stuck. You say, well, this just model isn't very accurate. It's not meeting our business objectives. What can I do? So let's look at some things we can do. So you look at this graphic on the left here, and this was when I was looking at that problem of predicting late flights, right? And so the data set that I started with just had the flight, the flight times and the airports, just a couple pieces of information. So that was helpful. I got some degree of accuracy. But then what I did was I actually looked at this paper that looked at all the different root causes, because I'm not an expert in this domain. I kind of did my own research on it. And I said, okay, well, weather, right? That's a very straightforward thing. And so I augmented my data set with BigQuery public data sets. There's a weather data set, and I could basically match and look at the airport code and then get some lat long from that, match that to weather stations, and then, be able to tell, is there snow, rain, hail, etc. Add that to the data set for a little bit more signal. And then you could see some of the other factors where you might say, okay, well, again, my model is doing better, but I wish it could be doing, even better. So you can see some of the other factors that may not be in your data set that you'll want to work with other stakeholders or somehow figure out, how can I get this extra data so that all the root causes I have included as features. So now if we kind of go to the right side, I'll just kind of walk through some of these issues. So what I talked about just now is really about domain expertise. Math and different hyperparameters can only do so much. Really knowing the problem, having experts that understand the problem, that might think creatively about how you're attacking it, is super important. So consider pulling some domain experts in if you don't have that expertise. Second thing, include more data, of course, more of the same data always helps, but also some varied data, training data, maybe different features and kind of some diversity there in your data. Feature engineering, right? With the features that you already have, is there a way to unlock a little bit more signal out of them with some transformations that you can apply to the raw data? Another thing to think about is that you might have some extra features that aren't really useful that you're overfitting on. Your model is basically locking in on some features that aren't really relevant in out of sample data. And so consider trying removing some of those. And alternatively, back to this idea of starting with a simpler model, maybe start from scratch again where you have a simpler model, add back in features, and just see if you can remove. Sometimes less is more. Of course, we can try different model architectures. Okay, well, you're using LSTM, maybe we try CNN, we try, different hyperparameter tuning, some ensembles. And finally, I mentioned AutoML before. Doesn't hurt to try AutoML to just see, are you in the right ballpark with how AutoML is doing? Okay, so I hope that helps. Let's move on to the area of transparency and fairness, a critical area. So, it's important that your model serves all of your users well, right? So thinking about these issues from the very beginning. And let's just kind of walk through a little bit of some of the questions to ask yourself about your model that may be implicit, but as you think about them, I think it will help your thought process, right? Around what problem are we solving? Who's the user? What are some of the risks of the model? And then how are you collecting the training data, right? So, many times we make mistakes by neglecting to include information, right? So what is your process to collect the data, and so on and so forth. This is a good way to kind of look at the whole process of building your model and looking at it responsibly, looking at limitations of it, and then after you built the model, continue to evaluate and monitor it. Now that you have some real world usage, where is it failing? Where is it not performing as well? And that's a lot. Those are a lot of questions to think about. So, we're continuing to provide more and more tools. There's a lot more that can be done. But I just want to point out a couple examples that might help you. One is the What If tool. And this is a really cool tool. If you haven't tried this out, you can include this in your notebook. And it basically has this graphical interface that will show up. You can use TensorFlow models, AI platform hosted models that we discussed before. And what this can do for you has a lot of capabilities. One is, say in classification, you'd be able to see all sort of the data points here, and you can look at changing some of the values and say, okay, what if I change this value from 10 to 11? Where does it move in the chart? Does it switch it from one class to the next? So it allows you to almost to sort of debug your your model and see how little changes matter. There's also something called counterfactual analysis, where you find for a given data point, what is the closest data point that ended up in the other class? So and then you're able to sort of compare, well, what were the differences, even though that these were determined to be by Euclidean distance or some metric like that. Theirs were very close, but what differentiated them? So this allows you to really dive in and understand your model better, the What If tool. Another option that you may want to look at, this is called TensorFlow model analysis. It's part of TensorFlow Extended, a set of capabilities that wrap around TensorFlow, the TensorFlow core framework. So what TensorFlow model analysis can do is it can slice the data and give you accuracy by different features. So what we're looking at here is a view of this taxi cab data set. This is a data set where we are predicting if there's going to be a tip of 20% or not. And there's a lot of features in this data set. There's the duration of the trip, starting location, ending location, et cetera. But what we're seeing here at the bottom is we picked one of the features, start hour. And you can see, at 8 o'clock in the morning, 9 o'clock in the morning, et cetera, what is the accuracy there? So we might be able to tell, okay, well, our model is not as accurate at 1 in the morning. Maybe we have fewer training examples then. Maybe there's something we can look into our model. So it gives you, again, a little more granular view of what's happening in your model, sliced by different features than by looking at just one number for the whole data set. Okay. So kind of related to that, it's helpful, one issue is many models are they're hard to understand, especially as you're using neural networks. And there's this trade-off here, right? That simple models, linear regressions are super easy to understand. You have coefficients for each feature in your model, but they're not accurate. So kind of you have this trade-off as you add more complexity, as you're trying to hit higher levels of accuracy, often you're adding more complexity to your model. So how do you explain how your model is doing? So there continues to be new enhancements to explainable AI. So there are libraries out there that you may want to look at, Lime and SHAP. And I wanted to also show some of the capabilities on Google Cloud for explainable AI, where we are doing some really interesting research that we've made available to users around all different kinds of data types. So you see here, even on image data, trying to figure out where in the image are the critical features, in text data, and then in tabular data, right, which is a common use case where we're coming back to the sort of here's a situation where you're looking at, it's this rental bikes. So we're looking at, based on distance and different factors, how long is a trip going to take, right? So you're kind of seeing in descending order. The longer the trip is, we're seeing, what time of day, the temperature, these were all factors, and kind of seeing in increasing order of, or rather decreasing order of importance. So that's explainable AI. It is available in multiple services on Google Cloud today. So we'll kind of looking at all the different sort of layers that are available to you. Let's just focus on a couple. AutoML. So when you train an AutoML model, you will see feature importance for the model as a whole. Also, when you send in a prediction, you'll see the most important features for that prediction. Likewise, with AI platform training prediction, when you create kind of a model that you're scaling to all of your users, you can turn on a mode where you're serving the explanations along with it. And the deep learning VM images and notebooks in Jupyter Lab now have the SDK built in for explainable AI. So it's even easier to take a model that you're working on and get some insights into it. One other new thing I wanted to point out as far as sharing how your model works, it's called model cards. And a model card, think of it this way, it's documentation for your model. It provides a clear explanation of what does your model do, what are the inputs, what are the outputs, what architecture did you use, what's the accuracy of your model, what data sets did you use to train and validate on. So it really gives your users a full picture of how to use your model and its limitations. So this is something you find out more at modelcardswithgoogle.com. I also wanted to point out the model card toolkit. So I actually wrote a blog post on this recently. I want to point out it works with TensorFlow, but my blog post actually talked about using with scikit-learn and basically how you can extract information from your model, use this model card toolkit with Python, and end up with a generated HTML page that provides a nice documentation of your model. So this is something new to check out, model card toolkit. Okay, so we've kind of talked about this journey so far from building your model, explaining your model, and then as we all know, that there's a whole nother set of challenges around how do you make sure your model process is reproducible, how do you scale your model. So let's start to talk about some of the challenges in sort of the intersection of DevOps and machine learning called MLOps. So This is a real issue. You could accidentally push a bad model into production. So if you're, working very quickly, you're experimenting, you're trying out new models, what if you accidentally deployed a model that wasn't tested properly? So consider something like a machine learning pipeline for this. Just like you with software code, you're going to have unit tests. You're going to have a system, in Google Cloud, maybe like Cloud Build or using Jenkins. It's going to run your tests. It's going to perhaps, automatically deploy it, etc. You could do the same with machine learning now. So here's an example with Cloud AI Platform Pipelines. You see on the right side, you create an end-to-end process that extracts data, maybe validates the data coming into your model, maybe the upstream systems feeding data, something changed, and now your inputs are a little bit off. You can also have an evaluation stage where you compare, is my new model better than my previous model? And then if so, push it to production. And then you may want to have some artifact tracking along the way, right? So each step of the process tracking, okay, where is the storage bucket with the input data? What was the distribution of features like you see here in the screenshot? All of that, being able to track and save that each time. So that will help provide some guardrails around your ML process. Because once your model is being used into production, this is real. Your model's making critical decisions that affect your users, and you want to have the same level of testing that you would apply in any other software product to avoid bugs. Another problem that's a little less obvious is this idea of drift, right? Where your model's doing great, then things slowly start to change, right? I mean, machine learning models often do hold for quite some time, depending on the domain. Some areas are, they can last a really long time. So think about like a text to speech, speech to text models. May last a long time, but a model based on news or maybe a product catalog would change really quickly, and everywhere in between. So the conditions that you learned from will change, and you're going to see that accuracy drift down over time. So what can you do about that? So consider a couple MLOps processes. One might be continuous evaluation. And this is where what you can do is on the prediction side or the inference side, just occasionally take a sample of predictions coming through the model, then manually compare to the ground truth. Have some experts kind of take those samples, assess the accuracy, and then raise a flag if you're above some threshold, right? So that's one thing you want to do, is to occasionally go and check those predictions, evaluate them. Another thing you may want to do, this is more of a preventative measure, is continuous training. So assuming that you have those guardrails in place, the testing of your inputs, your model outputs, et cetera, you may want to think about running on a regular basis, or when you have new data coming in, to kind of prevent the data from going down and becoming obsolete. Okay. And so speaking of model inference, the last problem I wanted to mention is scaling model inference, right? So we've got two very different workload profiles. Training is very spiky. I'm going to run this massive training job, and then I'm done, and I don't need to use the service for a while. Inference is very different. I'm taking my model code, I'm putting it into a production application, and although it's pretty quick to run a prediction, your application could have millions of requests coming in. So how are you going to scale if your model gets used all over the place? How are you going to host it? How are you going to serve all of those different requests? One option could be using the AI platform prediction service, where you can host your model, and then it can have auto scaling capability. So it will add more nodes to serve your model, and it can scale back down. It will handle the logging for you. You can also take advantage of specialized chips like GPUs. It's built on top of Kubernetes, right? That's where the scaling comes from. So definitely a good option if you're looking to kind of handle that variable workload on the prediction side and have the logging and infrastructure handled for you. Okay, so that kind of wraps up the 10 problems. I just wanted to point out a few resources if you wanted to find out more. Of course, the Cloud AI platform, this is the starting point for all the tools we talked about. Code Labs at codelabs.developers.google.com. You can Google that to find that. I should have probably put the URL in there, so apologies. That allows you to try out a lot of the technologies you heard about today. There's a machine learning section with a bunch of labs to try. Finally, we use YouTube quite a bit to discuss some of these concepts. One of the channels that's popular is called AI Adventures, where we've got over 50 YouTube videos talking about ML concepts as well as how to use the platform. And that's it. And we'll open it up for some questions and discussions. Feel free to add me on LinkedIn or Twitter to continue the discussion. So I will now stop and switch to discussion here.
Yeah, sounds good. First of all, thank you for doing the talk. It was pretty cool, and you did like quite an overview, right? From like getting the data right, getting idea to almost like production and actually bringing to scale inference, right? So like really cool that you showed like all of those pieces. And while people still kind of getting their head around the content and writing the questions, I will start with a couple of questions from my side. So you did mention AutoML, right? And it was like more in the section of I think you just like started with a simple modeler, right? And after one of the next slides, you were like, hey, and people can use AutoML without investing too much into the model itself, right? How do you see, like from your experience, especially with like maybe cloud users, right, or companies trying AutoML, do they take it seriously enough, right? Or does it feel almost like it's like a magical one-button solution, right? Because I do remember at some point I was mentoring some startups, and it was like a machine learning kickstart program. So like they should potentially have had a bit of like knowledge what they're doing with machine learning, right? But sometimes it's still a bit hard from, hey, we have business, right? Try to frame it like in machine learning perspective terms, right? And if you just give in like, hey, there's like auto almost like magical solution for your machine learning problems, right? Do they start thinking like more about how to frame problem, or is kind of becoming for them like too complicated and they're like, okay, so it just like magically solves all my problems, right? So where is the problems, right? How do you feel?
Yeah, it's a great question. I think when AutoML started, I think there was this idea that developers could just use AutoML and embed it into their applications, and that's it. You don't really need to know any data science. Now, I certainly think it has helped make it a ton easier and opened up ML to a whole bunch of more folks. I would still say, though, that it's really important to have some foundation in how to evaluate a model, right? Some of the concepts we talked about, like looking at a confusion matrix, then things that I think are available in a lot of the courses that are out there today. But I think it's opened it up, and I do think for experienced data scientists, it's a great tool because we're often so pressed for time that there's so many projects in this field. There's so many cool things we could do. I find myself sometimes saying, all right, I don't have enough time to, let me create a notebook from scratch and a new model from scratch. And let me try it out, see what I get. And often it's good enough. It really is. We've done some comparisons with Kaggle, and often it's, maybe not, been number one in the whole world in Kaggle, right? Keeping in mind that folks are working, weeks or months in teams and they're domain experts on it, but like giving this to a tool that has no knowledge of the problem, isn't reading the instructions, looking for little tricks. It's getting like amazing results on it near the top of the leaderboard. So yeah, I think really it's not a toy. It can be used for production. We have examples where we're actually including it in a pipeline, right? So combining a couple thoughts here is, yeah, it can be used in production. It can be used in a pipeline. we're actually working in Google Cloud of kind of integrating it even more. So it's not seen as a separate product like, oh, well, I'm doing my own, hand created models over here, and I'm using a different product for AutoML. It's just, hey, where's your training data? How do you want to build your model? Do you want an automated version? Do you want to do it yourself, right? So yeah, I think it's becoming more mainstream and unified, and I'm a big fan.
Yeah, I mean, definitely. I didn't mean that it's like just a tool or toy, right? Which it's definitely like very helpful, right? And for me, it's kind of almost interesting that it feels like that, there's like this joke that, 80% of your machine learning like task, right, to bring something into production is actually about like cleaning the data, right? And after like, another 10% or 15% is about like building pipelines, right? And like there's like 5% about this like exciting me building the models, right? And now we'd be like, okay, we're gonna automatize or like make it easier for those like 5% that everybody did enjoy quite a lot, right? But you still have to do all this like boring stuff of data cleaning, right, and understanding like all of this. So maybe at some point we need to have AutoML for cleaning data, right, or auto clean something.
Yeah,
right?
no, I totally agree. And I wish it solved that troublesome 80%. One thing that is cool though, it does have some automated feature engineering. So like sometimes what I see folks doing is like, say for example, your model, you might have a feature like is you have different results on a weekend versus a weekday. You have different call volume or hours or whatever. It will do things like you pass in one column that's like a date timestamp, and it's going to generate a ton of features out of that, right? It'll look at hours, months, years, weekend, all this kind of stuff. So it doesn't, get rid of that 80%, but I'm hoping, maybe it shrinks it a little bit. There's some of the, basic stuff. Of course, I mentioned at the beginning of the talk, in a large enterprise, sometimes it's even there's organizational issues, right? Where there's certain groups where they're holding the data, and you need to work with your management to explain the value of the project and work to do the data integration. Can't solve that yet, but certainly some of the more straightforward data transformations it will handle for you.
Yeah, definitely. And meanwhile, we got a question from one of the users. His name is, or her name is Fun, and asking, thank you for the talk, right? One question that, how would you handle ATL in GCP, data cleaning, feature engineering, etc.? I guess there's like many answers, but maybe for more machine learning, like heavy pipelines, right? I mean, it also depends if it's structured data or not, but how would you do essentially ATL in GCP? Kind of hard to answer, but if you can start.
Yeah, I mean, I think you put it well. I mean, there are a lot of options, and I don't want to overwhelm folks with the options. And I think that's an area that we can do a little better at explaining what tool is best for you. We did talk today about TensorFlow model analysis, part of TensorFlow Extended. So there is a TensorFlow transformation capability. That would be one way to do it, where you can, basically write some Python code, and there's under the hood, a lot of our products will actually use this technology called Apache Beam. That's an open source tool to kind of run these jobs at scale. So I'd look into TensorFlow Transform. Dataflow is another tool on GCP that's very popular for high scale jobs, like large batches or streaming jobs. Great tool. One thing that's new that's I've used that's pretty cool is called Cloud Data Fusion. I actually have a blog post on that if you Google it. It's a kind of graphical tool where you can take little boxes, nodes, and drag them onto a diagram and say, here's my source data. I'm getting it from BigQuery or a storage bucket, and let's do joins. Let's transform some columns, and then let's export to BigQuery or CSV or something like that. So that's a great way to get started. What's kind of cool about that is it will then run it on a Spark cluster for you. And again, you don't have to worry about the infrastructure. You click play, and it will set up the infrastructure. One other last thing I'll mention is sometimes you don't even need to do all that. In BigQuery, you could create views. So you could take your raw data and then maybe create a view on that where you're doing some processing to it, your joins across multiple tables. And so you have a view that's kind of the machine learning view on your raw data as well. And then you don't have to really go through all those data cleansing steps. So
makes sense.
Lots of options, but sorry, that was a bit long.
No, it's definitely, I completely agree, right? And I mean, if you have if you have like a more particular questions, you can always reach out to Karl on Twitter, and we can take a look like what is like more particular for your use case, right? Because you're doing like structured data, right? It's like one type of like pipeline. Maybe you want to just get it more regularly, and you do some things that gets like hundreds of gigabyte data like every couple of days, right? It's going to be a completely different scale. But I agree that especially with Beam, it's something that makes it easier. It doesn't really matter how much data you have, right? Because it's going to spin up like nodes in the background, and you're going to do processing for you. So definitely easier. So another question is coming from, I guess, Jonas. Jonas is saying TF Lite is really great for deploying ML models for offline applications. How much development is done for TF Lite? Especially, is there an option for encryption, password protection of your models? And I think the idea being that, your model, especially if it's like on device, getting shipped almost like automatically, and people may be afraid that if you're shipping it like somewhere, right, somebody can just like intercept and overtake your model altogether. Is there anything that you're aware of happening in this direction, or any research, or it's kind of like overthinking a bit?
Yeah, great question. I just want to say I'm not an expert on the mobile meets ML side. This is a whole really cool area that some folks on our team, they know they use TF Lite all the time. For folks who haven't really heard much about TF Lite, think of this as a way to take your standard TensorFlow model and create a smaller one. It uses some capabilities like quantization and other ways of sort of condensing the number of nodes in your model so that there's fewer parameters. And so it's really fast when you're doing ML on the device, ML inference on the device. And it has some other benefits like where I won't get into all those today. But it's super cool. It's worth checking out. I did want to also mention that AutoML Vision, we didn't get into that today too much. You can export a model as TF Lite, and if you want to run it on your device. So we're doing more and more sort of integration between AutoML and TF Lite. I don't know specifically about the password protection or encryption. I wouldn't be surprised if we had something like that. One of the cool new things that I don't know all the different TensorFlow libraries now. There are a lot of them. There's a ton of capability. One neat thing I was reading about recently was TF Privacy, which allows for basically some minor updates to, I believe it's kind of basically preventing with your training data, being able to know by passing predictions through it, whether a particular example was used to train your model. That's a little bit different than what you're looking at, but I'm not sure. I'd look at TF Lite docs, but it's certainly a very active part of development where, offline mobile use cases are huge in this field. But maybe in the future you can bring on have a mobile ML topic in this series.
Yeah, definitely. And maybe another question, and it's actually an interesting one. What is the name of a solution you would use to serve plain self-written Python models in custom-made dashboard or as an API? I guess like you mentioned that you have XGBoost, right? You have PyTorch and TensorFlow models that can be hosted. Can somebody host something, I don't know, like more custom basically, right? Something that's not supported out of the box, or you just like adding like more packages, and at some point there's going to be like more inference available from GCP?
Yeah, okay, so if I understand this question correctly, it's what if you're sort of creating something custom, you may not be using TensorFlow or scikit-learn. Mm-hmm. Again, lots of options. I'll mention a couple to think about. Let's start on the lighter, I think, easier side. Cloud Functions, if you haven't heard of that, is a neat thing on Google Cloud where you can basically say, here's a couple lines of code, just make it a function and serve it and give me an endpoint. And that's all it is. And then you have a lot of tracking around, number of requests coming in. It scales really nicely for you. GCF, Google Cloud Functions. If there's a, like sort of a code snippet that you want to turn into a little microservice. Another option is take that code and put it into a Docker container. And then you have capabilities like Cloud Run that will host your model. You'll expose a port for the traffic. That would probably be a little bit more robust approach if you had, a bigger code base. I'd look into that.
Pretty cool. Would actually, just a short follow-up on this one, would Cloud Run support custom resource allocation? Let's say, can you run Cloud Run or GPU to get inference on GPU, or is kind of a bit too custom use case?
I am not sure about that, but that actually reminds me that I believe I mentioned the AI Platform Prediction Service. It now has a pretty cool capability where you can run custom containers. So
nice.
I haven't done this myself, but you may be able to take your code and sort of put that on that service, and then I believe it's Cloud Run is a little more generic. That's kind of just for general runtime. It may serve your needs. There may be some interesting things that the prediction service can do for you if you use a custom container there.
Yeah, awesome. Thank you for answering all of the questions and for doing this amazing talk on Thanksgiving. Thank you again for your service to the community and making machine learning community as a better place. Yeah, with that, thank you again.
Great. Sergey, thank you so much for hosting. Everyone listening, thank you. Great questions. Hope to be a part of the group again.
Yeah, have a good rest of the day.
Thank you.
Bye.
Right.
Ciao. Cool. We done the first talk. We got really good overview, and now we're gonna go into really exciting stories by Anant. So please give him a round of virtual applause. Hey.
Hello. Hello. It was very nice. Quite interesting talk by Karl. And hello, guys. Anant here. Going to be take my mask off first. So I'm in the Google office currently, even though there's nobody here anymore. But yeah, there's a rule to keep masks on. So I'm going to quickly give you. So my let me try to see the screen. So my objective today would be to give you guys a run through of the experience of WTF experiences while going through. You thought the project was going smoothly, and then somebody pulled the carpet from below your feet, and then you realize a lot of your time, investment, and effort has to be then redone. And how do you deal with the setback, and what some of these, a couple of stories I'll go through. And how and if you face any, the idea is if you face any similar scenarios, these are some things which might be reusable across in similar problems. And I have on purpose removed the exact details. I'm not sure how much is shareable outside. So so I have used sudo. I've changed the problem a little bit to hide the details, but so that's give me a second. Sorry. That's what I have done. All right. Can you see my screen?
Yeah.
Can everybody see me?
It's working fine.
Great. Perfect. So so let's begin. Right. Let's begin with story number 1. And the story revolves around any image search problems or ranking problems when you want to find similar images, computer vision problems. So that's the first story revolving around. So these are just random images I have pulled from the net because I just wanted some objects. This is not the problem I tried to solve. But the problem was such, the use case internally was such that basically the challenge was, it's basically an image search use case where they're given an image, a query image, you'd like to find, let's say the most similar image or images, ideally a ranked list of images which are the most similar visually, and so on. And that was the problem. And normally this is a very well known problem that you compute embeddings, you do similarity, or you do classification. And so this is a well-known problem, but the challenge is that for this particular use case, for this particular project, there are thousands, not just thousands, thousands of different classes. And furthermore, there was a heavy imbalance amongst the classes, and the images were extremely rare. Some of the images were extremely rare, and it was not easy to source more images from different angles and more of the same kind. That was a constraint, and there was like with the heavy imbalance, some classes had barely a few images per class. Some of the object classes had only barely a few images per class. Another problem was that like they were extremely diverse. I made watches here, but of course not watches. It's like items. Let's assume you have exotic watches, right? If you're searching for a watch and you find like things like these, imagine if this was actually a watch. Is some kind of this is not, but I mean, imagine if this was a watch. Actually, this is a watch. So taking the watch example, but the actual problem was different. However, there was a similar aspect. Like you could, even as a human, you would have a trouble telling. There's so much high variance in the distribution amongst the watches, and so many, let's say, modes of in the visual data distribution, and it was extremely hard to generalize basically across classes for the model. And another thing was the latency requirement. The whole end-to-end computation that included serialization, sending, computation, and back had to happen under 4 seconds. Ideally, as less as possible, but that was the upper limit. So everything had to happen. So you couldn't use anything too fancy or a model which is like 100 billion parameters, because that just won't give you that kind of latency, at least not easily. And another one was that the accuracy requirement, like the minimum, and this was a top 5 accuracy in the top 5 in the ranking system, was 95%. This is the minimum threshold, like which was required for the project success criteria. So you can see less data, imbalance, fast, high variance, everything combined in one, high accuracy requirement. So this was a very a challenging problem to start off with. Now, since it's about ML horrors, I would like to go ahead with like the 4 horror moments. So and I'll explain each one of them in more detail after this. So the first approach is obviously like treat this as a classification problem, right? Thousands, like given an image, classify into one of the thousands of, like the last layer being a softmax distribution across all the classes, right? And put some kind of function approximator, be it machine learning or nowadays deep learning. You work on the model, you work on the hyperparameters, layers, use exception net, pre-train, fine-tune, whatever, but treat it like a classifier. However, okay, this would be SOTA, not SOTA. The state of the this is the first approach which I tried. However, it failed miserably. And the state of the art, the best you could do, actually, in terms of the accuracy requirement of 95%, it fell much, like far shorter of this. And so, okay, that was horror. What? The best thing you could try, the best classifier you could throw at it, was so much less than the minimum requirements. So this gives you a feeling of unease. Is this problem even solvable with the given data and constraints? Maybe it's just no way to solve it. Should we even invest further? So that's the first horror moment, I would say. Then the action taken, which was that, hey, try another approach. What I looked into is what Sergey mentioned initially, metric learning or like contrastive representation learning approaches to get a partial ranking instead of trying to classify across it. And get some kind of partially ordered ranking, which normally performs better in a high when the output cardinality is very high. I mean, this like thousands of classes, and normally performs better according to. So I talked with the internal research teams and engineers. Okay, let's look at this, and then okay, now implemented approach like best that was possible according to research and engineering, but it's still not good enough. It improved upon the accuracy by like 10% over the regular 5-10%, but it still wasn't good enough. So then again, this is horror number 2, because okay, now what? I've tried everything. Now, like, what else is possible? Shall I even invest more time and effort, or shall I just call this project a failure, that there's just not enough data signal in the data? It's just not doable, this problem. So, but before doing that, I was like, okay, let's look at another approach, and this specific to problems in which you have a lot of output classes, and you want to kind of divide and conquer this. Instead of trying to solve the problem in one go, why not divide the problem into multiple pieces and have different models, a multi-model setup, hierarchical setup, solve it. I'll go into more details later with a custom design hierarchy. And that actually improved the accuracy by a lot. However, there was also some of the data, then another horror which came in was that on the clean images, it performed fantastically. It actually met the threshold of 95%. It actually crossed it by a percent. And so it was huge improvement, like 30 plus 30, 28 to 30 points over the previous, the contrastive approach, over the original first approach. However, they were only on clean images, and there was often a lot of noisy, like with pixelated, all kinds of low light noise and dirty data coming in, which had like barely visible things, like barely visible objects. And so what now? This wasn't accounted for during the training process. So this was again like, oh my God, just discovered this by looking at the evaluation data, which it performed really bad on, by looking at the performance per data point. And then was, okay, so the idea, one approach which comes to mind is do data augmentation and include this in the training data, right? Include such artificially synthesized, noisy, and augmented images in the training data itself, which was done to a certain extent, but not entirely as noisy as the real world data. But the problem with that was that you could not really replicate, you could not possibly foresee and replicate all the possible scenarios which could happen in the real world. And secondly, it was extremely hard to retrain and get labeled images for those dirty data because we didn't have dirty data in the training set. So this will be an extremely prolonged and complicated process. So another approach which I tried was, okay, why not just use traditional computer vision image processing and look at the problems with the kind of typical problems with the data, analyze the brightness. I did some descriptive analysis using some image pipelines. What defines dirty? So is it noise, is it brightness? And figured out that the two major problems were the brightness was on various scales, and there was often noise, especially caused by speckle noise, caused by low light problems. So basically developed these before these dirty images were sent for inference, basically they were passed, there was a detection module which detected if it was noisy or not, and if so, applied the traditional hand-coded image processing, traditional non-machine learning driven brightness normalization and denoising code to make it easier for the model to do inference on, which improved the performance significantly on these data points. Am I still in the streaming? Am I still streaming?
Yeah, all working fine.
Okay, perfect. Great. I just wanted to ensure. All right. So, and then the fourth horror that happened was after all of this had been done, now the problem came that, hey, there's often new data coming in from the users. So users are supplying, in a way, new data, and this is and also data coming from other sources. Labeling such kind of data is very difficult, and you don't, and so it's very expensive, time-consuming, and difficult. How do we deal with like improving the model, however, without labeling it? So basically, you have some label data which was used in the training, and there was new label data coming. So that horror problem was solved via semi-supervised learning. So these are the 4 steps. Like, as you can see, it was step by step. You discovered you did something, you discovered something new, you try to solve it, see, and it's very easy to just give up in the beginning. It did seem like, but in the end, like after all the horror stories, like at the end of every horror, okay, not at the end of every horror movie, but this horror movie ended up well. So I'll not go into too much detail, but the approach number 1, which I talked about here, is just a visual representation, given an image, classify into 10,000, this is a random number, but it's like thousands of classes, just softmax distribution. Let's say the accuracy was X. Then comes the second approach, which was the representation learning with contrastive representation learning, and little intuition behind it. Basically, instead of trying to classify given an image and trying f of x and trying to fit the distribution of pass this through and get the predicted class, trying to narrow the distance between the predicted and the target distribution. Here, it uses the contrastive triplet loss approach. Instead of single images, it uses triplets. And what it does is there is a reference image, like the one on top. It's called the anchor, and an image which is very visually augmented but similar looking. So it's just like, say, a random augmentation on the original image. and that's called the neighbor, which is semantically similar, because I mean, just because this image has been randomly cropped doesn't mean that the semantics have changed. And another image which is so distant from the original anchored image that it's much more semantically distant from the original image than the neighbor. So the distant image should be much farther semantically from the anchor image than the neighbor images. So this one should be closer, basically, in the space, in the, let's say, cosine similarity, or in the search space, in the embedding space, basically. And so this basically tries to pull, this learning approach uses triplets to pull the semantically similar items, let's say, can be not just images, but can also be any kind of embedding, textual embedding, entity embeddings, graph embeddings, tries to pull them together and push the anchor and the distant image further apart to get, and it caused accuracy improve of 5 to, I think, 10%. I forgot the exact number. And I think, okay, this seems to be an issue with this slide. Give me a second. Okay, so there seems to be, give me a second, it seems to be, I have to refresh slide deck. All right, so then the approach number 3 comes first. Sorry for the order. So the approach number 3, which works the best, which includes more than 30% over approach number 1, was basically breaking the problem down into, first of all, extracting the relevant part of the image in case it's zoomed out, or maybe it's very small part of the image, or there's other objects to distract it, make it easier for the model. So do some image processing in case it's a noisy image. Otherwise, even for non-noisy images, extract the segmentation model to extract the objects of interest first, superimpose it on a white background, and then pass it through a hierarchy of classifiers, which basically material classifiers, and just given some names, like just imagine like materials gold, just making these up for now. But the problem was framed very similar. Category classifiers, which kind of deals with the category aspect, and this basically narrows down, because you are segmenting the problem into multiple smaller problems, and each model is then sharing weights for the elements which are common, like edges and corners, but then has its own set of layers which is trained separately on certain subsets of a data to only solve a much simpler binary problem. And all of these together, and basically are then all of these labels from all the classifiers are then used as a pre-filtration for a data efficient contrastive loss model, which was shown in the previous slide here. It was then used, and then this together basically improved the accuracy by a lot more. It's the same, the intuition is the same as if I was to give you, say, okay, you as a person, if I was to tell you, okay, distinguish between these 10,000 different objects and tell me which one this certain object belongs, which one is most similar to, and there's 10,000, you might get confused. Your performance will drop the more you try to learn. But what if I was to give, let's say, 2,000 of you 5 objects and say, hey, your job is only to distinguish between these 5 objects, the overall chained accuracy might be much larger. And this is essentially, so if you're dealing with a problem with a large sparse amount of classes with low amounts of like heavy imbalance, this is an approach you can use. And this also can be extended to NLP, of course, using, of course, it's not visual anymore, so you'll have to do the change some things, but the approach can then be extended to there as well. And the semi-supervised approach, I will not go into more details, but basically the approach which was implemented was inspired from SimCLR, the paper version 2, basically, which uses, which in a nutshell uses, it's a semi-supervised approach where it uses supervised data as well as unsupervised data to distill knowledge into a model, which actually, even just 10% of labeled data and 90% unlabeled data, it actually can outperform 100% label, a model trained on 100% labeled data. Yes, very counterintuitive, right? In this case, you can see this line here, it actually outperforms. And this was also reflected in so basically, it's 10 times more data efficient because it can achieve the performance with 100% label data with 10% or less. So this is what we use, and the gains weren't exactly this much because it's a real world problem, but it was still quite significant. And so this is how we solved this story. And before we go on, I'd like to stop for any questions, or maybe take the questions towards the end. I think that's probably better.
Yeah, I think it's easier because it takes for people a bit of time to get these questions right. So let's go with the second one, and after we do some of them. Yeah.
Exactly. So, okay, then the story number 2, I call it the Inception recommenders because I love Inception. And this was like you have a dream within a dream. This was a recommendation system for recommendation systems. So basically, and it's the approach to machine learning tech behind it is actually reinforcement learning, not supervised learning. And the context is such. Again, I've just taken this snapshot from Amazon, but this is not approach wasn't done for Amazon, and this I just taken as to explain the concept of it. So basically, if you go to an e-commerce page, you often in your home page you have like the problem wasn't the e-commerce problem as well, but I'm just exemplifying it. You often have like blocks, right? You have blocks where you have like each block is like there's a product recommender block where it recommends products, and then you have maybe an article recommendation, you have maybe an advertisement recommendation or whatever. So you have multiple blocks, and they recommend let's say each one can have different recommenders. So basically the problem was there are multiple blocks, multiple components, and each of the components can choose between 12 different or 15 different recommenders. And each one of those recommenders, once chosen, are then the individual supervised ranking recommenders, let's say X supervised ranking recommenders on their own, which then show you the items, right? So let's say they're X ranking systems, and the problem was which ranking system should I choose for which component? And the idea was to basically maximize the interaction, such that each one of those ranking components were actually supervised ranking systems on their own, but you have to select which supervised ranking system to show where, and basically maximize interaction while still staying relevant to the user, right? Don't be clickbaity. Just because you want to maximize interaction, you don't want to show things which are clicked often because that's not relevant anymore. So that was the use case, and I directly go to the solution first, and then go to the horror stories. The solution basically was the person, the user, basically coming in to interact with the components. Basically, we used so me and a few others. We went for contextual bandits, which is a simplified version of reinforcement learning, which is reinforcement learning with time step of 1. Look it up for those of you not aware. It's often used Google technologies as well. You see YouTube using it. You see lots of Play Store using it. And the advantage over supervised because it's now selecting the supervised algorithm to use, right? So we said, okay, the user, we need to know something about the user. So we used TF agents, TensorFlow agents, to implement this. And the idea was we need to know something about the user. And these are some examples I mentioned, like maybe the age, maybe the search history, maybe any kind of historical information, interaction history with the users. You need to know in order to personalize which algorithm to choose for the user. And then ARM features. ARM features are actually, there's a terminology used in contextual bandits, at least in TF agents, which basically says, because the objective was not to recommend a particular item, but a recommender, which then in turn recommends the items, you need to know what items the recommender is recommending. In order to choose between 15 different recommendation algorithms, you need to know what item each one of those 15 different recommendation algorithms is recommending, the top 3 items at least, to know, because the items are dynamic, right? The recommendation algorithm number 1 might recommend item 5, 6, and 7 once, and based on your history, because it's also personalized to you, it might recommend 10, 11, and 12 the next time. So it's not a fixed thing that you can just say, okay, choose recommendation 1, algorithm 1 all the time. You need to know what it's recommending, the top 3, top 4 at least, and not the complete list of complete ranked list, but at least the top 3, what the user sees, and need to know something about the user, and then basically embed these two aspects, the ARM feature and the global features, and say, okay, these ARM features are separate for each of the X recommender algorithms. If recommendation algorithm number 1 recommends 3 items which are different from recommendation algorithm number 2, let's say R of I, right? Then this global features, they call global because the user is the same for all the 15 algorithms, right? These will be then paired up with all the 15 algorithms, and this will be embedded, and all the 15 will then be embedded again and concatenated and be passed through a distance function to map it between -1 to 1, let's say, between 12 recommenders or so, which says 1 means great interaction, -1 means the user hates it, and 0 means neutral, indifferent. So that is, and then this you would say, okay, this is a supervised problem, right? How is this contextual bandit? Well, once the user embedding is then paired up with, let's say, let's say 12 different recommendation embeddings, you would get 12 different values between -1 to 1. However, we want to maximize engagement, right? This is where the reinforcement learning aspect comes into play. You don't always want to be selecting the best option, because often trends change and you don't always know if the option you're recommending is the best one if you haven't even tried the other option. And there's often a dangerous trend that certain behavior in one time period or group of users might bias the model to shift towards recommending the optimal action for them. And this will recommend towards all the users, but it will never try another option, which it could have been better if it had only tried. So this is the exploitation versus exploration of new opportunities trade-off. So here is where we applied epsilon greedy search, which let's say for the X recommenders between -1 to 1, some of the one which has the highest is the greedy approach, right? The one which has the highest, let's say, reward, the best approach, the best recommendation algorithm, it's chosen with a value 1 minus epsilon. So let's say epsilon is 5%. With a 95% chance, the best recommendation algorithm is chosen and displayed. With the epsilon 5% chance, randomly an algorithm amongst the 12 algorithms is picked and shown to the user. There's some amount of randomness because this allows it to adapt much more quickly to dynamic trends. Let's say if the pandemic hit and things changed, right? You want to adapt very quickly, and this allows the algorithm to be much more dynamic. So this is so in the interest of time, I'll just quickly go through the horror stories and go to question and answer. So the first horror story in this scenario seemed quite simple, right? This was the final solution, of course, but this is the modeling part. Dirty data and data problems are never are always the issue, right? So supervised learning, we first started off with supervised learning approaches. We realized, okay, no, not going to work. You cannot use a supervised algorithm to choose supervised algorithms. That's just didn't quite work because it wasn't dynamic enough. And besides, collecting label data there was often concept drifts, data drifts, which supervised algorithms, then you need to correct it manually, unlike contextual bandit algorithms. And then basically reached out to collaborate with the contextual bandit experts in the TensorFlow team and the research scientists in YouTube and TensorFlow team. So that horror was solved. They said, okay, let's try contextual bandit approach. Then now the world seems beautiful, right? Contextual bandits just implemented. Little did I know that actually there was a data bias problem. So there was a problem because the data we had per component, we initially thought, okay, there are X components, and each of the components have Y recommendation algorithms to choose, right? So each one has, let's say, 15 recommendation algorithms to choose from. So X into Y, the cross product, would essentially be the action space. Like you have to choose like a matrix where for which block, which recommendation algorithm should you choose. And this is how we frame the problem. And that's the optimal way to frame it because it accounts for the dependency between various blocks. However, there was not enough historical data to even warm start the algorithm, right? To warm start, you cannot start from scratch completely, it'll take ages. There's not enough data available historic. So we said, oh God, we designed it and we realized, oh no, not enough data to have this X kind of Y, this kind of large action space to choose from. So what shall we do? Okay, let's simplify it. Instead of choosing, okay, for each block of the X blocks, if you want to choose amongst Y recommenders, let's just do it block by block. Let's just do, for a single block, the topmost component, let's say, okay, let's choose amongst the Y recommenders, just 15 recommenders, let's choose amongst them, right? Simplified problem, lower search space, and this we did have data for. Great, now what could possibly go wrong? Well, this time around, learning from previous mistakes, we did some EDA, exploratory data analysis, and realized that there was far too much bias towards some recommendation algorithm than towards the others. And the bias was huge, not like 10 to 1, but more like 10,000 to 1 kind of ratios. And this would lead to already a huge bias, which will take a long time for the contextual bandit to correct. So this is not ideal. So we threw away that and said, okay, wait, we need to collect fresh data with a uniform random policy such that data is more or less amongst the 15 recommendation blocks, let's say 15, right? It's treats samples and shows the user randomly with equal probability. So by 1 by 15 probability, it shows the blocks and collects interaction data and wait a month or two till we have enough data. So there's a huge delay put. However, once this was a good choice, because once that was done, we could start the problem, start implementing as a solution, and yielded good results. However, another problem which we came up with was that we had not foreseen in the beginning was that often a lot of features which were categorical encodings of categorical features, they were very biased because some features were activating far more often than others. And furthermore, if there were new categories to come in, the whole model will have to be trained from scratch because the feature space was fixed. If you want not encode something, even if you embed it, it still doesn't solve the problem entirely. So we said, okay, we cannot leave that data, but can we use an auxiliary source of data which correlates with the information? And we decided to include textual embeddings which are present even for unknown categories, which are new out of vocabulary categories. And that will provide as an external source of information in case a new product comes in. And this was a final solution, which we're still working on, but it's so far giving good results. So that's it. And thank you. And that's my email in case you'd like to reach out to me. And now the stage is open for questions. No, you must have a lot of them.
Yeah. So first of all, it's like amazing presentation. Like it's really cool that it's not just theoretical problems, right? But more like shit, right? Not working anymore, right? Okay, like let me figure out something else, right? It's definitely something that people appreciate quite a lot. So we got a couple of questions, and well, YouTube is a bit of like delaying, right, for the people. I think we can give a couple of minutes for people to collect it. Yeah. So first question, I would just like maybe start from my side while we're getting questions. So you showed us like a nice ensemble of the models, right? And there's like a segmentation, and like some of them are like lighter. And I remember somebody was saying that you still need to perform it like pretty quickly, right? Were you still able? I mean, since it's like a success story, right? You were able, right? But how did you do it like so quickly, right? Because it was like any optimizations to run it quickly, or like in parallel, or what is it?
Yes. Oh, yeah. I forgot to cover that because there's so many aspects. Yes, this hierarchy, it was much bigger than this. I just made this hierarchy to illustrate the concept, and it was like hundreds of models here, right? And the hierarchy was almost hand tuned, many of them, like together with some taxonomy, like people who knew the domain. And yes, it was optimized. A lot of optimization was done. One of the major optimization here was running this not in sequentially but parallel, running all of these models in parallel and getting the labels and then applying post-processing on that instead of waiting for the first one, then the second one. That was a huge, let's say, latency boost, reduction. And secondly, caching, like so, and there's a lot of aspects in the caching part which we did as well, and also like optimization in terms of when the image comes in, like because we wanted the models to stay light, so we tried to optimize them, keep the models as small as possible to keep the forward pass latency as small as possible. So we optimized a lot on this, and yeah, it managed to meet like much less, half the time.
Nice,
So-
nice, pretty cool. Maybe just follow up to this one. Were you considering, or maybe some of the models, are they kind of like a multi-head models, right? So you have the same backbone, right? But if you have like two different branches to get like some part of the model, or was like too complicated and it was just easier to run many small models like in parallel? Like, was there like any multi-head ones?
So no, they were not multi-headed. However, they did share weights. So you can say, so for example, the right amount of layers to share was something we experimented with. Of course, it was like, so they were like, let's say if the model has X blocks plus Y blocks, the X blocks is common across all the models, which we saw, okay, we extracted the convolutional weights and saw, okay, which one of the X blocks have common features to the objects, like, and then Y blocks are specific to each one of those, depending on the decision hierarchy. And then we kept the Y blocks trainable, but they were not multi-headed. They were separate models. However, they did share a lot of common layers, which were frozen and not non-fine tunable. Those common layers were kept frozen to make it more data efficient.
Yeah, was it an explicit decision not to have it multi-headed, or just like you started from, just like a common blocks, right, and you just kept it as it is?
It made the scalability of this. It was explicit because now if we have to add 100 more models, or I mean, if you want to change it, changing one multi-headed model is far more effort. You can easily add and subtract models on as independent components. Yeah. So it was more of a design and convenience decision.
Yeah, and I guess it's also easier to train, right? Because you don't need to have the loss that does the same things. Yeah, cool.
Exactly. So you have separate training for each one of the components.
Yeah. So here's a question from Jonas, and he's actually asking, I guess like many people could have thought, right? It's like, hey, you have feature extractor, right, based on CNN, and you just like cutting off without last 2-3 layers, and potentially you get like k nearest to classify visually, right? Do you think it's why it's not going to working out, right? Because I guess you did mention there's like many classes and there's like heavy imbalance, right? But if it's like visually similar, right, would it still kind of, let's say like if you have 10,000 of one class, right, and very few of like another class, would it just like get too much of like neighborhood without actually knowing what is it, or where was like the biggest source of errors, like in such a simplistic approach?
So that's exactly what you mentioned is the reason why contrastive approach did not perform so well, because it was biased towards the dominant classes, the majority overrepresented classes, and the underrepresented did not get the love they deserved. So this is where, by separating this problem, you are ensuring that the majority, for example, the material which is most dominant, would be separated from the other. So then the bias would not creep in, because the algorithm would automatically adhere when there is less majority versus minority. When there is less imbalance, it will automatically take you towards the right decision point, which acts as a pre-filtration for the ranking model. So the ranking model will be pre-filtered. So all the majority classes, which we have correctly seen, that is not the majority class, it will prevent that bias from happening. One of the reasons we went with this approach was for this reason exactly.
Yeah, completely makes sense. Cool. While people are writing other questions, I will feel like another one from my side. And I guess, okay, so for me, it's like really fascinating, right? That like how extended you are. Also like, hey, okay, now it's not working. Let me figure out like what is lighting distribution, right? And what problems are there. Do you consider, or like, is it also like now a part of your checklist for image classification and be like, hey, before I jump on this one, right, I would like to see, distribution of the noise and like light beforehand? Or you'd be like, okay, let's run it first, and after, if I have a problem, I know like where to come back?
Actually, I'm always, at least it's my personal approach. I'm always trying to fail quick, then throw. This is where he mentioned, like, if there is a way I can figure out throw to see how fast, like, cover that 70%, 60% of the ground, and then go into what's not working. That's the approach at least I like to try, because you don't know what's not working. And if you over-engineer from the beginning and you realize it wasn't really a real problem, at least not for majority of the data, it is wasted effort. So despite that, I still now look at things. I'm always still visualizing data, and I'm looking at noisy data now, like learnings from this is like always visualize data bias and the noisy aspect before you jump the gun. Like with the recommendation system, there's so much time wasted when we had to recollect the data. If we had only done that EDA in the very beginning, like the project would already be over by now. So this is, but then again, I think it's all about trying to explore the search space as efficiently of things you could do as possible, while ensuring that you know that there's nothing more to be done, and when to back out and say, hey, that's all we could do. It's always a trade-off.
Nice. That's pretty cool. So maybe on the second question, right? So sorry, like a second story. You did mention like reinforcement learning, right? And before you kind of like even went to, hey, we have this like a data problem, I was like wondering, because in many cases, right, even if you have like your approach, right, still on one hand, like heavily biased by how data is collected, right? So in the ideal case, right, your agent should get like environments that are most like in the beginning, like randomly sampling like recommenders, right, but also recommendations from there, right? And you did mention that you were like recollecting the data like afterwards,
this one.
but it was still like not completely random, right? Or did they like allow you
to? It was completely random.
Oh, nice.
Yeah, did they allow us to from that point onwards? So the problem was historic data was much larger in volume.
Yeah.
So of course, collecting from that point onwards had the issue that we have much less data and we have to wait. However, we could decide then what kind of data we want and what kind of policy we want to collect it with. And the advantage was this, and it was the trade-off was worth it, because the amount of bias was far too huge to be useful, the previous data. So there was a conscious decision to not go like spend time and effort on the old data. But the good thing is the pipeline, which was on TensorFlow extended internally, was already made in parallel with the bias data. So when we know when the uniform random data comes in, we simply have to change the source. And a lot of work was still done in parallel, so not all the time was wasted as such. But yeah, it was still a horror story because we were like, what? We thought we had it solved. So yeah.
Coming from different directions, right, where you don't know it. Like how do you think now you like having experience with TF agents, right, and seeing is actually working like very nicely in production? Is it something that can work out only, with the size of companies that you work at, right, or like a tiny startup with, I don't know, e-commerce, like with a couple thousand items, right, can still get this one? Like because usually people like so afraid that for reinforcement learning, right, you need to have environment that you can play with, right? I don't know, all the Atari games, right, is because you can sample from environment, right, and get enough like action space, right, to record and replay like afterwards. So do you think it's kind of becoming more practical with approaches, contrastive bandits or whatever, like CBs that you said, or it's kind of like still a bit of a big guns in a way, or big companies?
I would say no. It's actually, when it comes to TF agents, it's actually the people I've worked with in the TensorFlow side. They implemented, I think, 40% of TF agents themselves. So yes, I would say it's not a big gun thing. Actually, it's so simple. The code, if you were to look at the model training code, it is TF agents especially. It allows you. It's like you can get the whole end-to-end done. You don't need an environment. You can also get the signal and everything from data itself. And you can wrap it around. It's very easy to use, and TF agents, especially with like 50 lines of code, you can have the whole RL environment plus agent training, everything done. So I would definitely recommend, unless you're doing something novel, like trying to implement a new algorithm other than the standard ones included in TF agents, then I would say use TF agents. It's very easy to use, and you don't even need to know what goes on behind. It even scales automatically behind the scenes with replay buffers. The scaling part, especially when used together with TFX, TensorFlow Extended, it's such a great fit. I'm just like, I'm glad I don't have to go into the algorithmic detail of each and every, because there's enough problems to be solved outside it.
Yeah, makes sense. Well, maybe like last recommendation of TF agents, because we even had it like on this meetup as well. Many examples when people solving games, right? And when you have actual environment, can you recommend anything that like our members can read up on how to solve it for a bit more productional use cases, right? We have like data points as you have with recommenders or with anything else, and you can apply TF agents for solving this problem.
Yeah, well, if you'd like to learn I would say TF agents, their tutorials, the examples given in a TF agents page. This is what I used also personally to get up to speed with it. They're literally like given, just copy paste with the toy examples, play around, and it's if necessary, look in the GitHub page to see what goes on behind the scenes. But as such, you can use this for games. You can use this for production environment. TF agents is meant to scale, so you can use it in production very easily. Yeah. I would say the golden combination is TFX plus TF agents. This pipe and everything is open source. This is really like can be used anywhere and is super scalable.
Yeah. No, I think it's a good example because at some point we also had like Robert from TFX team, one of developer advocates, and I think I'm not sure if he's watching that, but it would be like really good use case for them to show also to other people that like, hey, it's like combining also with reinforcement learning and other points as well. So really cool. Awesome. I guess I don't see like any questions coming in right now. So yeah, thank you again for having this amazing presentation. It was amazing pleasure having you, and yeah, hope to see you once like it's over with also like craziness with pandemics like in real life as well. Have a good.
Yeah, thank you, Sergey, and thank you everybody for joining. Have a great weekend. Bye.
Yeah, bye. Yeah, and everybody, thank you again for joining. I hope you found something like exciting and new in this one. So take care, stay safe, and do some TF agents. No, I'm kidding. Do whatever you want.